Allison Gray from NVIDIA. Can you please come to the stage? Allison is a solutions architect at NVIDIA, supporting customers using GPUs for deep learning. Prior to joining NVIDIA in 2014, Allison was a research engineer at the National Renewable Energy Laboratory, where she researched non-imaging optics for concentrated solar power systems. Ms. Gray has received both bachelor's and science and master's of science degrees in mechanical engineering from UNLV and a master's of science in imaging science from Rochester Institute of Technology. Allison loves dogs and rescued a retired racer. They both love running and training fast. Our next panelist is Douglas A. Palmer. May you please come to the stage. Dr. Palmer specializes in technology solutions, utilizing digital signal processing, high-speed digital network, application-specific integrated circuits, and real-time computer software. With over a dozen patents, he has founded several startup companies and is currently the Chief Technology Officer at New Edge. Dr. Palmer received his Master's of Philosophy and PhD in High-Energy Physics from Yale University. Our next panelist is Dr. Victor Lee. May you please come to the stage. Dr. Lee is a principal engineer in Intel's data center group and leads the HPC ecosystem application team, HEAT. He joined Intel in 1997 and has worked on Intel Pentium Pro, Pentium 4, and Itanium processors. At Intel Labs, he spearheaded Intel's integrated core architecture and for the first Intel Xeon Phi coprocessor product. His research interests are applications of machine learning, artificial intelligence, to solutions to improve HPC, and as well as revolutionary computer architectures. Victor is a senior member of the IEEE and has 40+ professional publications, 15 granted patents, and more than 30 pending patents applications worldwide. And our final panelist is IBM's Scott Sutter. May you please come to the stage. Scott Sutter is an offering manager with IBM's Cognitive Systems business, with responsibility for solutions in high-performance computing, high-performance data analytics, and deep learning. During his 20-year career with IBM, Scott has been a global cluster sales executive for high-performance and technical computing, a sales specialist for IBM's Unix customers, and Scott holds a BA degree in anthropology and an MBA with a focus on organizational change. Mr. Sutter resides in Portland, Oregon with his family, and in his spare time he enjoys fly fishing, amateur photography, and recreational swimming. And that's our panel. So to begin tonight's moderator question session, I'd like to start with a question that has always interested me and that I've always wanted to ask global leaders in this space, but finally we get an opportunity to do so. So every year, technological capability surpasses the imagination. How does this generation of processor technology differ from last year's state-of-the-art, and what design changes made this performance boost possible? Is it on?
Hi. Okay, so I think the question was, can you guys, I'm really short, so is it better if I stand? I think the question was, how is this year better than the last? So I'm new to NVIDIA. I've been here at NVIDIA for about 3 years, and I can tell you that some of the differences between this year and last year, in our hardware specifically, was just, I think the main objective internally at NVIDIA has just been a really big focus on deep learning and things we can do to accelerate that. And that, while that helps other areas as well, while some of the things we did helps other areas as well, I'll just highlight some of the key 5 things in in our new architecture. We have a new GPU architecture that came out called Pascal, and there are some really cool features in it. And one of which is HBM2, high memory bandwidth. The other one is every year we always improve our architecture, and that happened this year as well as it has in previous years. We've increased it so you get more computational power, and then we have a huge group of software people as well as hardware people that focus on not only improving our hardware, but also focusing on ways, a group of people who focus on ways to make sure that you can utilize all that power. Because we know there's two things. There's the hardware and then there's the access to it so that you can use it for whatever you're trying to do. My focus is deep learning, so my primary goal is to make sure that anybody who's using deep learning can benefit from all these new features and the new architecture, but the goal is also to have people who are doing general HPC things to benefit from that.
Yeah, with New Edge, I believe that the transition of chips is going to be away from concentration on compute and more communication. Today, I'll talk about that a bit. To do a 64-bit multiply accumulate is about 60 picojoules of energy. To get the data out of DRAM into the registers to perform the operation and back again is about 4,200 picojoules. So why worry about the compute? You're losing all your energy in moving the data. So there's going to be, pull it closer? Okay. Yes. So there's going to be a convergence of the network, the computing, and the memory. They have to work together. It has to be one piece.
Well, so let me see. So the question was, what enabled the chip to run better and faster, right?
Yes.
So I guess, well, I'm from Intel, so I should talk about Moore's Law, right? So we all know that Moore's Law is pretty much the driving force for putting more and more transistors on the same silicon, on the same area. And that more transistor has been actually giving us the performance edge so that not only just Intel, but almost all the silicon company out there is integrating and putting more and more features into their processors. Now, having said that, right, I'm sure you all hear Moore's Law slowing down. But at the same time, we actually hit a number of the bottlenecks, right? For example, we have thermal power almost 10 years ago, so that we cannot keep increasing frequency of the chip. And therefore, we actually have to go into more parallel design and having more and more so-called cores inside a processor there. And then the next challenge will be, as we actually integrate more transistors into the same chip, you will actually start getting into a fault tolerance problem. Well, transistor will fail. I mean, either you got a cosmic ray comes in and strike your processor and things like that. It's going to cause some problem in the chip. So how do you deal with when you have billions of transistors, if one of them die, can you still survive that kind of problem? Now, the other question that Douglas was pointing out is communication is becoming a problem, right? I mean, the amount of energy cost to actually compute a flop is actually much, much less than moving data around. Now, these are all definitely challenges. And of course, right, over the years, we've been putting caches into the design so that we bring the data closer and closer to the processor. And yet, the complication is now you've got many levels of caches inside your processor, and it complicates your programming model. So, the conundrum is that we got definitely a lot of good things going forward. We got billions of transistors to play with, but at the same time, there's definitely a lot of physical constraint as well as programming constraint. And we at Intel are certainly working very hard trying to solve that problem.
So I think in addition to all these excellent technical answers, I think there's a cultural thing that has happened over the past 10 years that's really enabled a lot of what we're seeing as a fantastic growth today in deep learning and machine learning. And that is that people have just been so pathologically afraid of throwing anything away from a data standpoint that we're sitting on top of this huge ocean of information. And so as we get to better processor capabilities, from my interest, better acceleration capabilities, and also importantly, that the ghost of the machine, and also the ability to tie them together with extreme bandwidth within the system, we really end up at a great confluence today. So it's very exciting. I think that has driven a lot of the advance and the evolution.
I'm afraid that none of the speakers were built by NVIDIA, Intel, IBM, or New Edge. So my apologies. I would actually like to skip over and have everyone do the presentations, because I think that if we do some presentations, you'll get a better sense of each of the panelists' products, and then you can see some of the newest lineup of their AI and deep learning technologies, and I think that will better launch our discussion and questions. So I think we can actually start with Allison. I have your slide up here, so when you have an opportunity, I think we're ready.
Okay, so I'm going to talk about our deep learning platform. I'm just going to go over it. I was told that I'm only supposed to talk for 13 minutes, so I promise I'm going to be really fast. But before I get started, I just want to introduce some of the other people here with me. I'm not the only person from NVIDIA here this evening. We have another person, Scott Ellis, in the back, and Mark Skinner right over here. If you are local to this area, they are local too, and they can help answer any of your NVIDIA questions. I know we got some networking going on today, so if you have questions and you can't get to me, please reach out to them. They are fantastic, and I'm really thankful to have them here this evening. Okay, so deep learning. I'm a solutions architect. I spend almost all of my time kind of interacting with people who are users to some degree, users or explorers in the whole deep learning space, and use the GPUs for deep learning. So I'm going to talk a little bit about our platform. But I'm going to stand over here, because I've got Nicole.
And Allison, if you can please speak up into the microphone. You know, maybe mine seems to project better. Perhaps we can swap.
Okay.
Let's try this one.
Speak directly into the microphone. I think that way it'll pick up best.
So you want me to slide the picture back?
So Jared is going to start.
Okay, so we've talked a little bit about how we've come to where we are today, and I'll just talk about this from an NVIDIA perspective. And okay. All right, we'll get started. Sorry, guys. Okay, so there's a variety of things that have been changing over time. You got in 1995, you got the PC internet, things have gone full into the cloud, and now you've got AI and the Internet of Things. And AI is kind of everywhere in a variety of different ways. So it kind of just depends on, I mean, I think it's all over the place, and it just depends on, like, we've got an AI approach, or a deep learning approach for almost for a lot of things that you're trying to do out there. Whether it's using Siri to ask where you parked your car, recommendations or similarity searching, right? I don't know, every time I get on Amazon, I feel like every time I look at something, it seems to go somewhere into memory, and then the next time I get on Amazon, there's 10 other things that are very similar to the product I was looking for. Also, when I shop on Amazon, it will do a comparison search between my product and like 5 other comparable products with pricing, dimensions, color, ratings by users, and so forth. And you can use deep learning. There are deep learning approaches for all of that. And then things as simple as Netflix.
Yes, much better.
Oh, is this better?
Yes.
Okay, sorry guys. I'm not used to talking into a microphone, so this feels a little bit uncomfortable. And then there's other things, right? Like I'm watching something on Netflix where I'm very interested in a specific type of video or a specific type of movie, and I want to watch more of that after it's done, of this type of style, and I find it really nice that Netflix seems to know. Like, because you like this, I think you're probably going to like these other things. I'm like, great, Friday and Saturday night are committed to you, Netflix. I really appreciate it. But aside from my personal entertainment, there's other things too, right? There are things that are touching our lives. The medical industry, for example, we're seeing a lot of activity there where you can apply deep learning to things. Processing medical images, there are other things. The same thing that you would, the same approach that you would use for object detection to maybe detect things in aerial images or detect things from a vehicle, you could still use you could use that same technique for a person who's maybe blind to help them see and prevent them from walking into a busy street or prevent them from walking into a person on the sidewalk. So there are a variety of ways to use deep learning and machine learning techniques as well to help you accomplish almost any task or help you be more effective at almost any task you want to complete. And then this just kind of gives us another example here that a few more examples that I wanted to show you guys about things that people are doing. I also kind of wanted to say, I mentioned Netflix, I showed a picture of like Pinterest, I talked about Amazon, but it's more than just being an industry, right? It's more than just the products I touch every day. There's a lot of artificial intelligence research going on in other places. I mean, we're seeing all these initiatives from automotive. We're seeing incredible amounts of research coming out of our academic institutions as well. I feel like at every level, there's some type of deep learning activity going on, and it is really impressive. I find what I can do with my iPhone to be incredible, but I also find what is coming out of these universities to be astonishing today. And it's just everywhere. So even from the things that I touch every day to just the things that I'm reading about. And I work for Media, we have GPUs, and you can get a GPU today in almost any platform. I use GPUs on AWS, I use it you can use it in Azure, and even IBM has a cloud platform that I've used as well. In 2015, we worked closely with IBM to sponsor the 2015 ImageNet competition and competitors. So if you were competing in the ImageNet competition or interested, and you applied for resources through us, you worked with me directly and with some of the awesome people at IBM on that. And then in addition to that, I would just say that like, if you're not in the cloud, there are a lot of other ways to get GPUs too. You can get them through your workstations. I have them on my laptop. We also have embedded devices I brought from my show and tell. So if you want something low power, we've got that too. If you want to do something on the fly and tinker. I think that a lot of you guys are really experienced in the deep learning space, but so this slide here may not really mean so much to you. You may already, this may be old news for you, but I thought we should have it here anyways, just because these are the deep learning frameworks and they're all GPU accelerated. If you are an expert in deep learning already, you're probably already familiar with all these and you use one or two of them actively. But for those of you who aren't, what I will tell you is it is super easy to get started. There are tons of tutorials, there's tons of documentation, and there are tons of ways to get started. So if you like Python, you can look at Theano, you can look at TensorFlow. If you're a Lua person, no problem, you can use Torch. If you're interested in almost anything, I think if you're an R person, MXNet has bindings in R as well. So there's something for almost every language out there if you want to get started with deep learning, and the documentation is incredible. In addition to like documentation, I would say that the documentation is easier to read than any textbook I went through my first time in college. So it's like that good. And then if you even have a hard time, there are Google user groups, there are forums, and there are these crazy, amazing students out there who write really good blogs about how to do something, and it's super easy to understand thing. So this is just a slide that kind of recaps our products and talks about, and just kind of shows. Can you hear? Okay. All right. And just shows the different ways that you can access the GPU. This is focused on our Tesla products, which would be things that go in a data center. We have a DGX, and this is a really cool system that we came out recently. This is a dual socket system, and it has 8 of our new GPUs in it, new Pascal D GPUs. There are a lot of really cool things about Pascal that make it really incredible and great for deep learning and other applications. One is the high memory bandwidth. Another one is NVLink. NVLink is a mechanism, is a NVIDIA product that improves the communication between GPUs. So if you are a multi-GPU user, you will be really interested in this because you get way more communication bandwidth between your GPUs. And Mark over here has a sample of it, so if you're interested in putting your hands on it, he has got one so you can see it. But we also have other things too. If you are in for your server, we have P40s and we have P4s. P4s are really cool because they're really small and they only require about 75 watts, so you don't need any external power. Okay. And I would love to talk to anyone in more detail later about our products. And am I low on time?
You have about 2 minutes left.
All right, 2 more minutes with me, guys. So, GPU learning or deep learning model. I do deep learning all the time. I talk about it. I even experiment with it, and I read about it. I focus mostly on student blogs, though, and hands-on tutorials, because that's really where I get my hands dirty on the deep learning stuff. But this is kind of this is kind of like our circle, right? We've got training in the data center, training with your neural network, and then you can do deployment in your data center, but then you can also do...
You could use the little clicker for, if you click it, there's a red laser right in the center. There.
Okay. And then if you got a device, so if you have a mobile device, or if you have a vehicle and you want to deploy something to that, this is one way you can do it, right? You can do all your training, all your heavy lifting in the cloud. So for those of you that maybe aren't familiar with doing deep learning, the training part is very computationally intense and can take a long time. So for the most part, I do most of that with a server in our like small cluster. But then when I'm done, if I want, I can deploy it on a mobile device, such as the device I had over there, or if you want to deploy it in a vehicle or something like that. And then you can update it too. So maybe you need to make some changes to your network. For those of you who've done deep learning, you probably know that getting a neural network that is well suited for your task is kind of an iterative process. And sometimes you can spend a really long time hashing out all those edge cases.
30 seconds.
Okay, so I'll just conclude by saying I would love to talk to you more about our Pascal products, and so would Scott and Mark. And I'll also tell you if you guys are interested, if you like NVIDIA and maybe looking for a job, we are hiring, and I have some cards that I'd love to hand you if you're interested in a position at NVIDIA.
Excellent. I'm going to put up your slots.
Great. I really welcome this opportunity. I have toys to pass around, kid. One is our chip, the second one is a board that goes on. Grabbed it from the engineers just before I came. Usually people can hear me without a microphone. So, first thing off, I want to say thank you. I'm in an extremely distinguished company here. We're a small company. We're fewer than 100 employees. And we have strong relations with the others. For example, NVIDIA, the lab where our chip was designed initially was at UCSD, where Sumit Gupta came from. He was the guy who guided NVIDIA from just a GPU company into deep learning and other applications. IBM, they fabbed our chip. It was at the IBM fab. It's now Global Foundries. I won't go into that. Okay. And Intel produced really the first multi-core chip in the world, and I was the one who put that into a product in about 2000. That was for video over IP. We pretty much pioneered that. So we've learned deeply from what these guys have done, and we've learned from their mistakes. This is actually click. Okay, so this is our team. We were founded by Dan Golden, who was the chief administrator of NASA for 12 years. He put the space station up. He thinks big. He's a visionary. He found me at UCSD. We're a network of people. We're actually about 12 years old now. So we've been out there in stealth mode. What I'm going to show you today has literally not been revealed outside of our own company and the government. So, but I love talking about it. So here we are. So next slide. To us, machine learning is all about scaling. How well can you scale up? And I'll tell you why in a second. Next slide. Let's look at the neurobiological computer. Everyone calls this wetware. Okay. Let's look at the size scale we've got here. I'm not going to get too close. From flatworms up to humans. Look at the scaling. It's the same neural basis in the mammalian nervous system, but you're going from a few hundred neurons to hundreds of billions. What's the scaling factor we achieve in processors today? Factor 10? The littlest arm to the biggest arm, or the littlest Intel biggest? We don't scale with architectures today. Now something else I want to point out. All the fantastic deep learning you're seeing today is recognizing pictures and things like that. It's amazing. We're as good as fruit fly. That's all the better we're doing. Years and years and years. I've been in the neural network business for approximately since 1986 with HNC. I was director of engineering there. So Dan set out to say, if we really want to go up to human scale and thinking machine, what is it going to take? So there's more than you can digest here, but it's big. It is really big. So you're looking at billions, trillions, quadrillions of connections. That's the point. Thanks. So you're really looking at an absolutely phenomenal performance. It's got to be packaged in a small space because speed of light is an issue on a thing like this. So let's look a little bit about what it takes with existing architectures to achieve that. Well, the first thing you're fighting is this thing called the redshift. Logic has gone faster, better, more of it. But getting the data to it has not improved much. So at the top, you're seeing latency for DRAM, on the bottom, you're seeing it for logic. That's called the redshift. That separation is a disaster. As I promised, to do 64-bit multiply at 64 picojoules to get the data out of DRAM to do the operation 4200. You're blowing all your energies moving the data. So we decided to rethink it. Not so much from the standpoint of silicon, but from the standpoint of the architecture of the silicon. Next slide. So where do we look for an example? Let's look at the mammalian nervous system. What do we see here? Literally an infinite number of connections. Wow, it's the connections, it's the communication, okay? Adjacency of the memory and the processing. And heterogeneity. How many threads are in there? There's over 100 billion threads. How many threads do you operate today in most machines, particularly CPU machines? Not many. So heterogeneity, lots of threads, lots of communication. So we made up some rules for how we were going to change architecture and computing. One is scalable, heterogeneous parallelism. Okay. Heterogeneous, keep that in mind. Every neuron in your body is doing a different job in a different way, computing in a different way. Proximity of memory and processing, obvious. Support for complex connections in the hardware, not in the software, in the hardware. Drive the architecture of communications and push the information through. Not one neuron in your brain is requesting information. Everything is pushed. Data flow, data flow. Last, you have to operate with noise and failures, as was pointed out earlier. So we took that recipe through to an ASIC. Two rules of thumb and designing for the future here. One is you don't bring the desktop processor up into your cloud bring the cloud down into your processor. Okay. Second one is most machine learning is really digital signal processing. When it comes to an application, you've got to do a lot of DSP on it before you can really start thinking on it. So this is our processor. It's a bit strange. The center of this is a router designed by a mad router designer that we have who designed for Broadcom and other companies. It can move about multiple terabytes per second. It's 1 by 2 millimeters. Multiple terabyte. It drove the IBM Foundry crazy. At the top, the chip communicates through 16 10 gigabit per second bidirectional high-speed serial links. It looks more like a router than anything else, but below that is the computation. What we have is 32 small secondary routers, each one attached to 8, I call them TDSPs, or tiny DSPs. They're attached to the memory. We're running over a terabyte per second bandwidth on the memory. There's 80 megabytes of memory on that chip that you see there. This is our 3-year-old design. We're coming up with something much better. So another unusual thing about this, the clock tree in most chips today is the thing that is the biggest sink of power. There's no clock tree here. Everything is asynchronous. This is pure data flow. Everything just pushes through the system. Everything is based on flip communications. From the TDSP, through the routers, all the way up, these chips just glue together. You put more and more and more and more together, and you just keep putting more. We put 500,000 chips, 128 million cores. Now the interesting thing about it is, when you send data from one TDSP to another one, an entire data center, much larger than we just saw at Scale Matrix, you're talking about less than 200 nanoseconds. That's register to register. Many people, like InfiniBand, quote numbers, but it's to the bottom of the cache pool. Then it takes a long time to alert up to processing. So we do everything in flip communication and nothing else. We never switch modalities of communication. In addition, we have a control plane. We don't trust data flow for synchronization. We really have a control plane that can regulate everything that occurs internally down to the nanosecond, literally to the nanosecond. That avoids contention in the fabric. Next slide. Next slide. So the TDSP itself is an interesting little guy. This is called an EPIC architecture, explicitly parallel instruction processor. Each instruction dispatches to NPU and FPU, something like that, to perform the operation. It then advances to the next instruction, the next, and it keeps farming out what it wants to do. At the end, you can do wait for logical and collect it all together and proceed. You can dispatch a packet to anywhere else in one clock cycle. So the upshot on it is, we take our chips, you glue them together any way you want, you wire them together in a data center, and then you say go. And within a millisecond, the entire thing, the topology of it, is memorized and shot back to the host for downloading and synthesis in the first millisecond. So it doesn't matter how you wire them together, they come up and are cognizant of what you've got. Go ahead. So the ASIC that I passed around somewhere here, 2 minutes. Looks like this. Now the interesting thing is, the TDSPs are sitting in little blocks of EDRAM, which is a brilliant IBM invention, very low power, very high speed memory. They're actually the same size as a human neuron. Just kind of interesting. They're very tiny, 256 of them. The chip itself is quite large, but it's mostly filled with RAM, and that overcomes one of the problems we have today in silicon, which is it tends to overheat in small areas. So we fill it with RAM that doesn't generate as much heat. So what I'm kind of getting at in the architecture here is its attention to detail. You can come up with a brilliant architecture, but little tiny details, every picosecond in moving it here is a delay that slows the whole thing down. So you have to watch everything in the design. Next slide. So, performance. When we crank this up, for example, for the power and everything else we're getting, and this is the last generation chip, we're getting 3 times better performance on a thing like K-means clustering than any of the competitors. So, I won't name them. Okay. Next slide. So, in conclusion, basically, we call it a fabric. We call it lambda fabric because it's a lambda calculus type machine. It scales from wristwatch size to multi-data center size, same software, same modality of communication. So we think we've reached this scalability, and our next generation should push the limits a bit more. So one last slide. So it's basically a router on steroids. It is a cloud on a chip. And that's the way it operates. So you don't think anymore, don't think chip when you're thinking, think the computing fabric. Ultimately.
Thank you, Dr. Carlin. Thank you so much. Our next presentation is going to be by Victor Lee from Intel.
Well, good evening. Thank you for having me here, and I'm so glad to see so many of you here actually share the same belief that AI is going to change the change the next how we actually do computing. So I know many of you have great ideas how to use AI to actually change our life. So I'm not going to talk about that, but instead, I'm actually here going to talk about what Intel is going to offer to actually help you realize this kind of ideas. Wow. So I guess PowerPoint didn't really do a great job. Anyway, let me try to tell you what the slide's supposed to do. Well, we need some AI here. So to start with, Intel has this vision of saying, if it's smart and it's connected, it is best with Intel. And in this kind of vision, we actually put AI right in the center of it, because we believe that with artificial intelligence, it's actually going to change how people actually do compute. It's no longer just your laptop or your big supercomputer hiding in the cloud. It is actually all computing device that's actually sitting in your pocket, or you actually wear them on your body itself. And here, Intel is really, well, we are really invested, and we are really focusing on how do we deliver the best product, both hardware and software tools, as well as training, to actually help customers like you to actually realize your ideas of how to apply AI to change our life.
So this is a slide of hidden layers, the text that is in hidden layers behind it.
Yeah, okay, well, so next time I need to really test the presentation before presenting. So Intel actually uniquely offer a stack that actually go all the way from just a portfolio of lots of different kinds of processors that goes into from processor that in the supercomputer, to processing your laptop, to processing your phone, to processing your watch, and potentially things that you can wear on your body, to a lot of the software stack actually on top of it. I mean, the impression is that Intel is a silicon company, but the fact is that we're actually more going towards a solution company, and we believe that hardware and software coexist together is the only way that we can actually deliver the value to our customer. So the next. So let me start with, obviously talking about our processor. We actually provide a gambit of processor. From the left, we have our Xeon processor, which actually exists in almost every server in the world. And in fact, it is actually the most commonly used platform for doing machine learning today. I mean, because just imagine, there's just so many of them out there. To the next one, which is our Xeon Phi processor, which actually is our high-performance computing chips that goes into many of the world's supercomputers. It is actually designed with the fact that we want to have high compute density together with low cost and low energy efficiency. Low energy cost and high energy efficiency. So in the sense that they actually allow us to power up a very large supercomputer with a reasonable amount of power. To the left, to the right here, we actually have two new members of our family here. On the top is our Neuron chip, which we call them crest as our code name. It is actually a deep learning accelerator designed from ground up, specifically to accelerate deep learning, especially in training phases, to actually allow it to close to near real-time training capability. And then the bottom of the right side, it's our field programmable processor, our FPGAs, in a sense that for customers who actually have your own custom ASIC or custom IP block that you want to put into your product to make a differentiation, before you actually build an ASIC of it, you can potentially use the FPGA, and if the costs work out, you can actually potentially ship the FPGA together with your product and then have your own custom IP sitting in there. So, I mean, because of the time constraint, I'm not going to go into each of the processor and talks about, what's the features of it. But I think for the sake of interest here, we will talk about our two newest members of it. The first one is crest. It is a Neuron chip, as I mentioned earlier. It is actually designed from ground up specifically for deep learning capability. And as we know, many of our processors, as we look at the whole spectrum there, from a general purpose processor where you need to do well in many, many different applications, to a very, very specific ASIC. In the ASIC size, the main focus there is performance, very low power, so that you have extremely high efficiency. And the crest family is exactly one of those processors. In the sense that it pack a lot of, so you ask me, what is the most important computation going into deep learning training? It is the multiply add. So the crest processor will pack a lot of them inside this ASIC there. In fact, it's going to offer the most amount of compute density that all the processor has to offer. And I cannot disclose to you exactly how much it is, but it's going to be an amazing amount. In fact, it's probably going to be orders of magnitude bigger than any of the chips that we know today. Now, the other thing is, just having compute is not sufficient. Being a computer scientist myself, I design many chips. I know if I just put the holding power and multiply add into my chip, this is not going to be enough. We need to be able to feed this compute, otherwise your chip is not going to be any useful. So for this particular chip, we actually, again, also put in a new generation of very high performance memory on die. In fact, it's going to have 32 gigabytes of those on die memory. Together, it will offer about a terabyte of bandwidth going from this memory to the processor. Now, that's a single chip, right? As Douglas talked about, we cannot just do the training in a single chip. In fact, to do anything in real time, we need many of them. So how do you interconnect them all together? So this particular chip, at least the first generation of it, it's going to have 12 of the bidirectional interconnect that allows it to be connected to neighbors within the same chassis, or potentially to other similar ASICs on another chassis itself. Having 12 of these bidirectional high bandwidth interconnect really allows it to have a very, very fast communication. But of course, right, from an energy perspective, it's still going to cost you. But this is the best way we know how to build a system today. So can we go to the next one? Okay, so enough about the crest family. The next one is our FPGA. Currently, we offer this Aries 10 FPGA, which is sort of our top-of-the-line FPGA field programmable processor. As I mentioned earlier, the key thing about field programmable processor is that if you have some special custom IP that you don't want to share with other people, but yet you want to ship it and differentiate your product, this is the best way to put it in your product itself. Because it is programmable, so as you change it, you can have an upgrade path going forward and say, now I have an upgrade to change to my IP, but yet the whole platform doesn't have to change. Now, it is very energy efficient. In fact, when we actually look at putting some of the deep learning, especially image classification, to run on this particular chip, compared to all the other processors on the market, it actually gives us the highest performance per watt metrics in there. So can we go to the next slide, please? So here, just give you some basic ideas about this chip's performance, right? So in fact, we're going to have two versions of the chip. The discrete version, where you actually have the processor, you can sit onto a FPGA card, a PCIe card. That you can directly program, in fact, for something like an AlexNet, for doing image inference. You can get up to, using single precision, using single precision data type, it can actually get up to close to about 600 images per second for only about 30 watts. So you can actually see it's actually very, very low power for very high performance. But if you're willing to drop it down to a half precision FP16 type of capability, in fact, the performance is going to double close to about greater than 1,000 images per second for only 9 watts more. It's only at about 40 watts of capability. So together, it will give you the 25 images per second per watt type of capability. Now, we also have a product that actually takes the FPGA and combines it with the Xeon processor on the MCM package that you can actually drop into your Xeon socket, and then with the same socket, not only have the Xeon processor, but also have the FPGA processor there for you to do your custom IP. In this particular cases, because it's integrated, we have some more power constraints, so the chip runs a little bit slower, but they still get a pretty reasonable, close to about 600 images per second at half precision. Right. Next slide. So a new product in this family here is what we call Canyon Vista. It's going to be coming later this year. What it is it's actually the AES-10 FPGA sitting on a PCIe card, but at the same time, it will actually be shifted with Intel's IP for image recognition. So this particular product there, if you'd be interested in doing, let's say, video surveillance, security, recognition, and face recognition, and so on, this will be a product that you can directly buy and plug into the system, and it will automatically already do this kind of processing for you. It will come with the card, it will come with the custom IP, as well as some software for you to interface with your software itself. Next slide. So, talking about time frame, right? So these are the things that we are going to offer for 2017. From the Crest family, it's actually coming out later this year, together with the Canyon Vista, which is again a deep learning appliance in some senses. Everything is everything in the card that you can buy and plug into your system. On the Xeon 5 line, we're actually going to have a new Xeon 5 processor codenamed Nightmills. It's specifically upgraded for deep learning, so that it will actually perform probably, I would say, more like 4 times faster compared to our current Xeon 5 processor, specifically for deep learning. And then again, for our Xeon 9, we're going to have our next generation processor, codenamed Skylake, coming out, I think more like in the middle of the year. And then again, we will have a Skylake processor plus the FPGA version. So therefore, you do have a choice of many of the Intel chips possibly to helping you doing machine learning and AI type of applications. Next slide. So that's just only the bottom layer here, right? This is the type of processor that we are offering. And on top of it, you can see there's a whole stack of software that actually need to, so that we can actually build useful AI applications. So on top of the hardware, we have a lot of layers. We have a lot of what we call performance library, starting from our Intel MKL, which stands for Math Kernel Library. It put a lot of the scientific computing kernel, and we have a version of MKL they call MKL DNN that specifically have the routines in there that are targeting for deep learning, deep neural network type of operation. And then on the other hand, we also have something called Intel DAO, which is the Intel Data Acceleration Library. So it is for data analytic operation for a lot of the classic machine learning type algorithms such as k-mean, ALS, and so on. So those are already optimized and sitting in the DAO library. And on top of it, of course, we will enable all the common framework, the ones that you know and love. For example, Caffe, Tiano, TensorFlow, MXNets, and so on. And then, of course, we will have to add in our latest things from our Nirvana folks. We're going to have the Neon system also be a part of that. Now, on top of these framework, we also provided what we call the productivity layer. So we have something called Intel Deep Learning SDK, which essentially is a GUI that actually helps people to explore deep learning topology, and then the tab is actually our trusted analytic platform. So I think I'm out of time, so let me just put one more foil. So the only other thing is we're going to have this thing called Nirvana Graph Compiler coming out, which essentially is how we see interconnect, taking all the different kinds of framework and be able to map them down very efficiently into our hardware. So I guess I'm out of time, so I can't really elaborate more, but find me afterwards and I'm going to be happy to tell you more about this. Thank you.
Wonderful, thank you so much. And just to tell you, right now we're going to finish the last presentation, and then we're going to do moderator questions. We're going to continue with them. We have about 5 or 6 questions, and based on time, we plan to give about 30 minutes of question and answer from the audience. So I think that's going to be a very interesting part of the presentation. Okay, and now to introduce Scott Sutter from IBM.
So thank you, Tristan, and thank you, Feel Matrix, for hosting us tonight. This has been a great event, and I really enjoyed hearing from my fellow panelists today. This has been very, very enlightening. I am from the part of the IBM cognitive business that is not Watson. Right? So IBM spent the last 5 years trying to drill in everybody's head that Watson is machine learning and machine learning is Watson. Not that. But what I am doing is I am running a piece of our business today that is focused on one of what I think is the most interesting segments of machine learning today, the deep learning business. Next slide, please. So look, everything's changing, right? If you haven't seen some version of this slide, consider yourself lucky. Every single presentation I've been in, and I promised every single presentation I've given will have a slide in it, but I think it really talks to what is a pretty interesting technology phenomenon today. We are seeing this expansion of this vague, ill-defined term of AI into something that's been very, very functionally oriented. And we've seen the growth of machine learning as a set of technologies really take advantage of what I talked about just briefly earlier about this huge stockpile of data that's out there. That's really been the enabling technology today. And we consider ourselves very fortunate that we are at a point where the capability of acceleration and the capability of compute power are allowing us to actually do something with that data today. So at the same time that machine learning has been growing and evolving, we've seen a new technology, which is really this evolution of machine learning, deep learning, emerge. And with it comes the capability of applying neural technologies and neural software capabilities against traditional machine learning problems. Why is this interesting? The level of precision that this is the spot right here. All right, I think that the level of precision that we can get at algorithmically through the use of these neural networks is exponentially greater than where we've been previously with machine learning. And so we're seeing this very, very rapid adoption of deep learning as a methodology. I think right now, and I trust these numbers, we've seen deep learning growing at about 65% year on year in terms of adoption. So it's a fascinating place to be. Next slide. So what's standing in our way right now? We are seeing a rapidly evolving and greatly growing ecosystem, and this has impacts on stability. I think what's fantastic is so much of this is taking place out in the world of open source, and that has certainly been a business that my personal business has been deeply engaged with. There are challenges with that. Trying to tie together 100 different open source packages to try and build a TensorFlow environment today is nothing short of maddening. The next major issue that we are running into today, the skills are scarce. Having people with knowledge of data science, having people who can think about data as a building block for addressing an enterprise problem, addressing a research problem, those skills are few and far between. And so it's wonderful to see this room here of folks that are interested in this and are working in this field. We're hiring. We're dying to find this sort of skill because our customers are dying to find these skills. We've had a lot of interest. We've had a lot of excitement out in the industry, but people are stalling.
because they can't get the hands on to actually address the problem. And then there are really some structural barriers, I think, that we struggle with today. The software tools are complex, doesn't scale well. Much of the software written around deep learning tool sets, written in a manner and time where it's logically very expensive to pull data from memory into processing. We're trying to address that as well. And then also, as we look at the broader adoption, that second or third wave of adoption of these technologies, lack of support, lack of infrastructure skill around this is really standing in our way. So IBM's approach to this, and where we've stepped into the deep learning world, is something called Power AI. This is free. You can go download this today. You can go download it tonight. Power AI is a package of precompiled open source deep learning frameworks sitting on top of precompiled open source deep libraries that accelerate the capabilities of deep learning. It's simple to install. When we embarked on this journey last year, it took our team about 2 months to build a really good scaling working environment. We have simplified this installation, we've simplified this deployment into something that you can have up and running in 45 minutes, 3 commands. We hope that that removes one of those barriers to adoption. It shouldn't be that hard. My boss, Sumit Gupta, likes to call what we're doing here being the Red Hat of deep learning. Red Hat likes that we're calling it the Red Hat of deep learning. They enjoy the hat tag. The whole infrastructure here is built upon IBM's power processors and NVIDIA Pascal P100 Tesla accelerators. Next slide, please. So our goal was really to address a heat map what we thought the most popular deep learning frameworks out there were. We're looking at frameworks that are aimed at image recognition, such as Caffe, scientific analysis, such as Theano, Torch, and then the fastest growing, most popular framework out there today, TensorFlow. Version 0.12 is in Power AI today. Version 1.0 is in Power AI next week. We built this all, like I mentioned, in a single precompiled delivery. We've put the source up there. If you want to go to the project pages, you can pull this down and see what we've done. And we would invite you to take a look at it. We think we're doing some pretty interesting work around scaling, particularly as it relates to memory handling and utilization. It's all designed to take advantage of IBM's accelerated servers and infrastructure, and it's cloud ready. You can run it on those power servers that are sitting right next door in the Skill Matrix data center. Next slide, please. So, why does this work? We've done something interesting, and this is a statement about a culmination of work that we have done along with NVIDIA and Mellanox over the course of the last 3 years. I'll admit we were lucky. About 3 years ago, we embarked together on a project to build an accelerated computing node that sort of broke the barriers to bandwidth. We believe, as NVIDIA do, that connectivity is key. We believe that applying that bandwidth, that peer-to-peer bandwidth between the GPUs themselves and the GPU and CPU are critical. In data-hungry applications, such as deep learning training applications, if you can't get the data there, you're hitting the wall. You're failing to scale. So in our architecture, we've really focused on that bandwidth between GPUs and between GPU and CPU. This is a unique architecture. It's only available through IBM and our open power partners such as Penguin Computing, Supermicro, and others. What you'll see there is a very balanced system, and what you'll see there is a very logically flat system. And this is where I think there's an opportunity for innovation. It has been expensive to get data in and out of memory. What we're trying to do here with this architecture is flatten that capability. We have customers right now that are blowing through the capability of their simulations. They cannot run fast enough. They cannot run clearly enough on the memory available on GPU. By taking advantage of this flatter architecture, using something called Page Migration Engine from NVIDIA, you're able to actually coherently and directly map system memory across the entire system. We think there's a tremendous amount of opportunity for innovation here, particularly as we look at larger models, larger data elements that sit within models. And I'd invite you to talk with me about this afterwards. I have some ideas. Next slide, please. So, it's out there. This really, IBM has the Watson product, which is fantastic, but that's a buy. You purchase the machine learning capability by the API. This is really aimed at folks who want to build. And in particular, we're really focused right now on folks who want to innovate around this capability. We're looking for partners, we're looking for folks that are hitting a performance wall and are interested in exploring a new way to address deep learning architectures. And that's it for me. I'll be here.
All right, excellent. So now we're going to continue with the moderator questions. I'd like to get some lights on if somebody can take care of them over there. It's the second one from the last. Excellent. So you raised an interesting point about IBM's offerings, and I wanted to start actually by asking a question about cloud versus local processing. I think this is something very interesting for our audience members. What are the pros and cons, and how will this balance shift in the future? Local versus cloud processing.
Well, I think the balance has shifted, right? I mean, we are in the era of the cloud. That said, it's very expensive to move data. It costs you a picocent a bit to move data across a wire. Real money out of your pocket to buy bandwidth. Some of these data sets that we are working with and our clients are working with today, there are security considerations. There could be a lot of precious information in there. And then some of the training sets are just pretty damn big. I went and visited a client and I came back with a bunch of disk drives in my bag because the cost of actually moving it over the wire was going to be greater than the benefit of running an RM cluster. So I think you kind of pick and choose. IBM will always talk about a hybrid approach. We want to sell servers, right? No secret. We would like to sell servers. But we think that there's a lot of benefit, especially if you're looking at places where your data is adjacent to cloud processing capability. We think there's a huge benefit there. And we would certainly look to our partners like Scale Matrix as a way to help our clients grow and find the amount of accelerated computing capability that they need.
Hello? Okay. Well, so I guess there's a business answer, there's an academic answer. I'm not sure which one I should give. But, I mean, from the business point of view, certainly like Scott was saying, right? Cloud, it's definitely exploded, right? In a way that a lot of things is being processed on the cloud, but certainly there are constraints and concerns, right? Like security, how do you move a large amount of data over there? I think from an academic point of view, it's that in order for compute to be everywhere, the local computation has to come out. I mean, especially the edge computing. Because you just cannot process, upload all the data. I mean, as Douglas is going to say that, that's going to cost you an arm and a leg just to move your data up there. So there will be going to be a lot of local processing happening there. So I would say, from an academic point of view, it's actually shifting towards more balancing, that you will going to have more and more local computation, but yet you will still rely on the cloud to do more things for, how you look at the overall scope of things.
Yeah, I concur completely. Our customer base, some of them won't tell us where they put things, but to a great extent, private servers in a small cloud for some of the customers, and up in places like Amazon also.
So I'll just kind of echo what everybody else said. And I'll just say from personal experience, everything they're saying is true. And when I talk to someone directly, it's a balance, and it just depends. If you have a lot of data, and you can utilize hardware in the cloud. I generally like to do it, but but when I'm doing prototyping, or when I'm talking to someone about prototyping, it's usually with a small subset of data, and they'll do it locally. Some of the challenges that at least from people that I talk to, some of the challenges they have is sometimes people are intimidated by the cloud, or maybe they're on a cluster and they don't feel comfortable with the scheduler. So that's when I say, okay, let's get you started rolling and going locally, and then while you're doing that in parallel, let's get everything you need up into your data center or the cloud, so that once you're ready for that, everything's there and you're ready to go, and we can support you as you transition. There's that, and then, so that's doing like a workstation locally, and then in the cloud, or maybe the data center that you have locally. And then there's something like this, where this is kind of like a strategic plan, or this is part of your workflow, because this is a low power device, or other people will have low power devices as well, where you're always going to have some amount of processing on the fly here. But this is just another piece of the puzzle. I think it just happens everywhere, right? You're going to have some amount of processing happening at every level.
So, thank you for the answers. And I actually would like to direct another question towards you, Allison, because I've been following NVIDIA's progress through video gaming for a very long time, and just wanted to ask, what are some of the other industry applications which this technology will achieve in the next 2 to 3 years? Name some specific examples of companies and sectors which are experiencing paradigm shifts and disruption as a result of your processing hardware.
Oh my. Okay, so this is a really big question. I guess things that I've seen recently, I think in the autonomous driving is probably where I'm seeing a lot. And even in the medical industry, I'm seeing a lot too. Autonomous driving, gosh, like so many car companies now have these huge initiatives. I mean, Tesla has been around, but I think Toyota has an initiative. There are other car companies out there that have this like deep learning, machine learning initiative. And Audi's even got something, there was a collaboration with us in it. So I think you're going to see that pretty soon. In the medical industry, I think we're seeing a lot of activity just because there's an abundant amount of data. We talked earlier about people just kind of hoarding all this data and sitting on it and that opportunity, and I think the medical industry is another place where you're going to see that. Maybe what kind of, the impression, I'm not in the medical industry, so I just kind of hear things from people, but the impression that I have is that there's a lot of sensitivity around data, around medical data, because it's very personal, and so that might have been something that was kind of holding things back for a little while, but I think that we're getting really good about understanding how to use this data effectively and not negatively impact an individual person, use it for deep learning, use it with our products to change things, to solve problems, to help people, specifically in the medical industry. One thing is like identifying cancer more effectively at early stages, or identifying mutations that will lead to cancer more effectively really early on to help save lives, things like that.
And would anyone else on the panel like to chime in on this particular question?
So we have a customer who is actually, they are very heavily using computer vision and machine vision, and they're using it in a very non-traditional sense. They are a utility company. They have a huge infrastructure. Early on, they were an investor in drones to try and fly drones across all the power lines in their service area, and they rapidly ran into a problem that, well, now we've got hundreds of thousands of hours of drone video and nothing to do with it. So we, luckily they are also pack rats, they're data pack rats like many folks, and they have this huge infrastructure of data covering what are broken, breaking, degrading components of their utility infrastructure. They're able to train on this very quickly. So now they can view the drone imagery in real time. They can run inference out at the camera and say, go up hole number 20, because that's where things are happening right now. This has a direct human impact. Utility working is one of the most dangerous jobs out there. 20 people per 100,000 per year die. So they're really reducing the impact on their workforce. They're adding a lot of efficiency into their capability. They know what they need when they climb up that pole. And we're just tremendously excited to be a part of that and help them get there.
Sure. So, would you like to answer this question?
Well, I would just want to add a couple more from the HPC perspective. So a lot of the national labs that these days are actually looking at, well, so one of the reasons we build supercomputer is so that we can actually do more simulation, right? So you increase the resolution, increase the time step so you can actually simulate a bigger system and so on. But then they're starting to realize that there is a limitation to how big a system that you can actually build, right? I mean, building it is one thing, but paying for the electricity bill is another thing. So they actually are looking into using machine learning to augment the first principle simulation science. And then how the two systems actually combines together, it's going to open up a new way of how we look at science together. So this is definitely one trend that I'm seeing a lot happening in the HPC side. And then on another front, actually more on the neuroscience side. In fact, Intel has been partnering with Princeton University. You actually have a new institute of Princeton that actually look at using fMRI to actually image the human brain and trying to see how people think, using that technology and saying, when this person look at, let's say, an apple versus an orange, which part of their brains actually lights up? And this actually generates a huge amount of data. And with the recent advances in computing, in fact, both in terms of new hardware, higher capability, higher compute capability, as well as change in the software algorithm and so on. In fact, we actually speed this up. Previously, people think that at the current resolution, which is about 1 micron resolution of the brain, will take 44 years for you to actually analyze the data on the computer. We actually speed it up almost to real time. In fact, we speed it up about 10,000x. And now we can actually do the same level of imaging and same kind of analysis in less than 2 minutes. And again, the goal is for our next generation processor, we're hoping to actually do it real time so that they can actually look at your brain and trying to figure out what you're thinking. That could be dangerous.
Feel compelled.
Sure, of course.
One of our customers, I won't name, they have 57,000 people in IT. 57,000 employees in IT. They're fined multiple billions of dollars every year from theft. It's finance, of course. Finance, insurance, it's absolutely huge. It is intense manpower, security, theft, malware, the whole gamut. They need robo-adjusters. They actually want to replace humans with computers.
Excellent. Thank you so much. Would you like to chime in? Yeah. So we just spoke about all this power, hardware, and algorithmic. What are the major barriers do you see to the adoption of deep learning in broader enterprise from your perspective? We can start with NVIDIA.
Okay, so I'm really customer focused. I talk to people directly. So when I give you a response, this response is based on the people that I'm talking to. Some of the challenges that I've seen. Some of the challenges that I've seen. One, which was mentioned earlier, was just expertise. I talk to a lot of people who are kind of just getting started. They see all this excitement about deep learning and they want to hire people and they can't find them. Okay, is this better? Okay, that seems to be better. So expertise, it's hard. And I think it takes a long time. Deep learning, it's kind of deep stuff. If you break it down on a really simple level, it's just if we just want to talk about the image CNN part, it's a convolution. If you know your Fourier theorem, sure, it's no big deal. But you start combining all these things together, and then you start reading all these papers, and you're like, this is kind of an empirical process. These guys that got good networks, was this like a shot in the dark or what? So expertise, finding people with that expertise, and then just doing whatever's going to make sense for solving a problem. I think that those are a lot of the things that I come across during initial engagements. There are challenges later with data locality, how to get it there, how to utilize your hardware, all of your hardware. Like make sure that everything in your system, each system you have is working as hard as it possibly can, getting as much performance out of your CPU and GPU entire system architecture as possible. That comes up later too.
One of the issues we've seen in adoption is inflated expectations. We all have those. The other one are very, very simple principles like stationarity of the data. You know, what's that? It's an absolute key to making anything work. A lot of this has to be automated. Knowledge capture and moving along is absolutely critical to all of this. So we're trying to push this down to a 10-year-old level. So our product announcement will go later this year, but we're trying to move deep learning to a very low level where kids will start it, absorb it, and grow up with it.
Well, I think I agree with Allison in that, deep learning is actually hard. When you hear everybody say, oh, AlexNet is so great, and all the different CNN and so on. When you're actually going to try it, you realize it doesn't really tell you what you want to hear. And so, I actually think education, how do we actually teach people, make people aware of, what is this technology can actually give you, and how can you actually use it? It's actually there. So, if I actually up-level it into, what exactly is the problem, I think it's really productivity. How can we actually make the programmer, I'm sure all of you sitting here have some idea that you think, oh, if I can have that, that will be great. Now, how do you take that idea, going from an idea to become a real product? How can you minimize that effort? How can you actually lower the barrier? I think that is actually going to be the sort of the barrier to adoption. I know a lot of companies, including Intel, is actually trying to lower the barrier. There are so many frameworks out there, right? Every day there's only a new framework that says, okay, well, if you use this framework, it's going to be easy. But again, right, so how do you go, choose your tools so that it can actually do the job for you? I think, again, I would just say, we need to actually work a lot with the academics, with the university, so that we can actually train people and let them understand how to use it.
Absolutely. It's fun when we all agree. Education is key, and we're actually really excited as we see a lot of universities beginning to invest more in data science as a domain. I think that is going to help us usher in the next wave of this technology along. I think that there's also there's a fundamental opportunity for creativity. There's just an immense amount of software between training something on a deep learning training system and having an inference model and actually integrating that into something that's helpful and useful. And so that's where I think that the opportunity for thought leadership is today, to use last year's term, thought leadership. And so I think that that's a place where the creativity of the folks in this room will open up a tremendous amount of innovation.
Thank you. So I have one final question. Then we're going to allow Chris to tell you a little bit about Scale Matrix. And then we're going to get to the question and answer session from the audience. So get your questions ready. So the final question, and I've heard a lot tonight about various companies hiring, so I wanted to put it out there. I imagine that many of our members would be interested in applying for positions at your companies. Please tell us one awesome thing about your company that almost no one outside of the organization knows about.
Well, IBM has about as many people in it as Luxembourg, so chances are you know somebody. It's a fascinating company. I've been in weird corners of it my entire career, which in 2 days is 20 years, which I never thought I would say something like that.
But it gives you an opportunity to work globally on some of the most fascinating projects in the world. So I would invite you to look at where IBM is applying some of our research and some of the capabilities. And if you are a global citizen, this is a very good place to be.
Okay, wow, challenging here. One cool thing about working at Intel, I would say you get to sometimes look at what these chips that you make and be amazed how many transistors in there. We're always looking for the best and the brightest. And then in fact, I mean, I actually have been at Intel for 20 years. And for this last 20 years, I actually enjoy my journey every single day in the sense that I actually move around a lot inside Intel. It's a big company. It gives you lots of different opportunity. I go from designing a chip to actually doing some research and then come back and design a chip to actually go and write software and then to go and talk to customer and come back and actually look at what are some of the challenges that we have to face and then what are the things that we need to go change. I think in a big company like Intel, potentially IBM and many other top companies, there are lots and lots of opportunity. Again, if you're interested, if you have ideas, you will have the opportunity to explore and try something new.
I think the really awesome thing with us, we have free hummus and pita chips 24 hours a day. I think lately the most, our company is much smaller than this audience, so it's up close and personal, everything you do. But I think one of the awesome things, everyone from New Edge, raise your hand. Oh, not bad. Okay, it's half the company. Okay. One of the awesome things actually is we're 100 feet from the university, and we're bringing over lots of interns, so we have fresh, young ideas constantly flowing through. Really love that.
So can I say two things?
Of course.
Okay, so the first one is we have an open dog policy, or you can bring your dog to work. I take my dog to work every time I go to work, and I love it. It is amazing. The second thing is that it's like really weird. This is gonna be really salesy, but everybody's super duper dedicated in a really good way. Like in a way that I never thought was possible. I worked in a national lab before where everything was very like regimented and structured and you got your funding cycle and proposals and blah, blah, blah. And like NVIDIA doesn't have that. I've never worked at a startup. So some people say it runs like a startup, but I can't really verify it. But people are like really dedicated. I could send an email out at 11:30 at night and somebody will respond. And they kind of smile while doing it. I know, and it's weird. It's not like we don't like work or live to work. We're still working to live, yet we're still getting a lot of stuff done. So I would say that's kind of like the second cool thing.
Excellent, thank you so much. And when you guys have a chance, we put a binder over there of some of our members' resumes. One of the goals of the Machine Learning Society is to help our members to transition into careers. Whether they're 20-year veterans or they're just getting into it, we know that many of the audience members here tonight and the panelists, of course, have corporations that are looking for talent. Whether it's a startup or a large Fortune 500 company, our members have excellent resumes, and I encourage you to take a look and see if they fit your profile for what you're looking for. So I want to thank the panel. I appreciate your coming tonight, and you're still going to answer some questions. But first, I'm going to introduce Chris for a moment to tell you a little bit about Scale Matrix and this genomic facility behind me.
Appreciate you all coming tonight. Hope you enjoyed the tour of the data center. What a great panel that we've got here today, and it's really exciting to have all of you guys here as well. Scale Matrix is a 6-year-old business, but we've been operating in this space for almost 20 years. And the data center that you saw today during your tour was built because we had a vision that we would be pushing compute and deep learning and artificial intelligence and things like that to a degree that traditional data centers may not be able to support. So 5 years ago, my partner and I got together and we developed the platform that you saw today. It's called Dynamic Density Control. And I can tell you, we were early to the party. What when you launch a 52 kW cabinet in 2011, people ask you what you're doing because file services and web servers and things like that don't put out a whole lot of heat. And so it was a little bit of a labor of love. It was a belief in what we believed was the future. But I can tell you this with absolute clarity that as 2016 rolled around, and as our 15th year platinum partnership with Intel and our new relationship with NVIDIA and our friends at IBM and the folks at Dell and everybody putting out new servers today that are more powerful, help you do more, in a smaller footprint. Now our data center is now becoming extremely relevant for enterprise customers when they're trying to deal with the thermal loads and the heat abatement that happen trying to deal with the new workloads that we're facing today. Taking a page from each of the folks up here, we talk about reducing barriers to entry, making things more attainable and maximizing performance. Those are really some of the core values that we have at Scale Matrix, and some of the things that are really near and dear to our heart. We've been very, very fortunate. The company's grown significantly over the last 6 years. We're the leading data center provider in the Southwest market now. We have a platform that allows you to do things that you can't do in other data centers. For some of you that were on the tour with the folks from Scale who are here in the audience today, they showed you a box where there were 11 servers that have 8 GPU processors in each one, pulling down something close to 40 kW worth of electrical load in a single cabinet. Try doing that somewhere else in the country. It's a pretty tough trick. So we really love the fact that we can do that here. On the other side of things, as far as breaking down barriers to entry, the verticals that utilize the services that we're talking about, machine learning and deep learning, they span the gambit. But in San Diego specifically, we relate back to the life science and bioinformatics space. Behind me, you see a laboratory that's part of our accelerator program here at Scale Matrix. The building that you're in today is the Scale Matrix Life Science and Technology Launch Center. It was opened just about a month ago on January 10th, and it was the brainchild of the folks at Scale Matrix, our team, when we started realizing how many of our customers were getting into deep learning, artificial intelligence, and how many of them were focused on the life science and technology sectors. As innovators, as early stage companies, great ideas are coming out of our market today. But some of those barriers to entry is around office space, the cost of building laboratory services, data center resources, compute resources are sometimes really hard to come by in those early days. The idea behind the Launch Center was to be able to provide a cradle-to-grave support network for early stage innovators who need a place to call home, a place where they can store tremendous amounts of data and get access to large-scale compute platforms, a place where as an a la carte service, you can run in a CLIA-certified genomics laboratory and do next-generation sequencing operations. All the things you can do to take something from an idea to a commercial platform much, much more quickly. This is not an area where Scale Matrix plans to make a tremendous amount of money. It's an area where we plan to seed the community back with something as we've done extremely well over the last couple of years. It's kind of our homage back to the city. But after being here for a while, we hope that folks will learn that being able to get access to, as a service compute platform like NVIDIA's new service, our storage platforms, and the a la carte genome sequencing services as well are going to help people take their ideas from early stage to commercialization much faster. So I hope you guys have had a chance to meet some of our staff today. Any questions about Scale Matrix or would like to follow more news about the company, about some of our new platforms, sign up for our newsletter on our website, grab one of our cards or sign up. We'll be happy to keep you guys informed. Thanks for coming tonight. Keep pushing the edge, because the more of you that come up with great ideas, the faster that data center gets full. So thank you guys all very much.
Chris mentioned the word community, and as I look around tonight, I can see that there's so many familiar faces, but there's also so many new faces. We are growing, and I can see everyone here is excited about data science, machine learning. So our goal is definitely to join their companies if they're offering right now, but the ultimate goal is to make them feel like they need to come here to San Diego, right? That the talent exists here, and they're missing out if they're not placed physically in San Diego. So that's our goal, and we're going to accomplish this. It's going to take several months, maybe a year or so. Well, it already happened. It already happened. We are already the center for artificial intelligence research. Many people just don't know about it yet. Okay, so that's our mission, and definitely please Make them come. Okay, so now we're going to get to the question and answer session from the audience. Please raise your hand if you have a question, and I'm going to hand you the microphone, and you can ask our panelists any of the questions that you have. Any questions?
Hi, thank you for the fantastic presentation today. I'm a student at UCSD, and my name is not important, so I'm just curious about what is the most challenging customer requirement you have met in the fields related to machine learning. Thank you. The most challenging customer requirements?
They can, okay, my most recent challenging customer requirement. It's gonna be in the weeds a little bit, and it wasn't really a big deal, but this is because I interact with customers directly. My most recent customer challenge was actually a simple fix, and it had to do with missions on a data directory. And it's only challenging because I'm remote and I do everything on the phone, and I'm telling them command line. I'm asking them to run things through their command line and give me feedback. So I will tell you that the most challenging thing for me is verbal communication. The specific thing was a person who was telling me, I have this data in this directory and I can't load it, but I know that it's there. What's going on? And you guys laugh, but because it is, in hindsight, it's always funny, but at the time, this poor guy probably spent like 45 minutes trying to figure out what was going on. It was just a simple permissions issue. And when he gets on the phone with me, I'm like, okay, you're sure the data's there? Let's double check our paths. Let's do tab autocomplete just to make sure. And then do a copy paste. Maybe we've got a weird misplaced space, or you got some backtick in there you're not seeing the resolution of your screen, who knows. But those are most challenging because they're actually simple fixes. It's about really effective communication over the phone. You don't have TeamViewer or Google G-Chat to share desktop. It's all about talking about things. And if you're not familiar with the command line, you gotta take it slow.
I think our challenging customer has always been the U.S. government. Requirements like it has to run for 6 months on a battery, running a teraflop, and buried in the ground. Locations undisclosed. Other things like, well, we want to run half the traffic of Washington, D.C. through a box that you wouldn't notice when you walk by. So we got an unusual request, and so I said, meeting inflated expectations is always a challenge.
Okay, just listen to both Allison and Douglas. Mine isn't that bad. Like, so essentially, customer come to us and say, okay, can you run for higher performance? Okay, that we can, but lower power? All right, we can do that. How about cheaper? Well, can it be free? Okay, so we have to stop.